Okay, good morning. So this is the topic about discrete probability distributions. Okay, so I'll just proceed with the first speech. So discrete probability distributions. Okay, so there are some given here. So binomial, multinomial, hypergeometric, negative binomial, of course geometric, and then Poisson probability. Okay, so let's first discuss binomial probability distribution. So here in the binomial probability distributions, so it involves repetition of number of trials where each trial can result in some event of interest occurring called success or not occurring, which is called failure. Okay, example of each is tossing of a coin 10 times. So we can say that success is head and then failure is the tail. Then the experiment consists of repeated trials. Okay, each trial results in an outcome that may be classified as a success or a failure. Then the probability of success is denoted by P, remains constant from trial to trial. So the repeated trials are independent. Okay, then the expression, okay, or the experiment performed n number of times, then the probability of getting x successes out of the n trials is given as you can see here. So that is the probability of x success is given the combination of number of trials and the number of success, and the probability of success and the probability of failure. Okay, so n is denoted of number of trials. Okay, x is denoted as number of success in n trials. Okay, and then pre is denoted as probability of success, and then q here is denoted as probability of failure. So q can also be solved as 1 minus p. Okay, that it can be solved using that formula, the value of q. Okay, so in mathematical equation, that is in the formula of combination. Okay, so n factorial all over x factorial, then multiply by n minus x factorial, multiply by probability of success and the probability of failure. Let's have this example. Okay, so 80% of the graduates of a certain university who apply to a particular medical school are admitted. So 80% of the graduates, so probably these 80% are the probability of success. Okay, this year, 4 graduates from the said university have applied for admission to the medical school. Find the probability that 2 of them will be accepted. So the number of trials based on the given n is 4, okay, and the number of success, okay, is given as 2, and the number of failure is also 2, because there are only 4 graduates and 2 of them will be admitted, and the other half or the other 2 will not be accepted. Okay, so based on the formula, that is n is the number of trials, which we have given here as 4, and then x is the number of we call this success, so which is 2, and then this is the probability of success, which is given as 80%. Okay, and then q can be solved as 1 minus p, so 1 minus 80% is 20%. So substituting those values, we'll have 4 as n, 2 for x, and then probability of success is 80%, which is equivalent to 0.8, and x is 2, and then Q will be 1 minus P, which is 1 minus 0.8, that gives us 0.2, and then N minus X, so that is 4 minus 2, that gives us 2. Using your calculator, you'll have an answer of 15.36%. So that's the probability that two of them will be accepted. Okay, so moving forward. So here in the example number 2, the probability that a certain kind of component will survive a shock test is 3/4. So that is the probability of success that the component will survive. Okay, and the probability of failure that it will not survive is 1 minus 3/4, that gives us 1/4. So find the probability that exactly 2 of the next 4 components. So 2 will be Rx and 4 will be Rn of number of trials. Okay, using the formula. Okay, so N is 4 and then X is 2. Probability of success is 3/4. Okay, and X is 2, and then 1/4. Okay, that is the probability of failure, which is Q, and can be solved using 1 minus P, 1 minus 3/4. Okay, so that gives us 1/4. And this is N minus X. Okay, so 4 minus 2 is 2. And using your calculator, you'll have an answer of 21.09% is the probability that exactly 2 of the next components tested survive. Okay, so here's the problem number 3. Find the probability that 4 tosses of a fair die, the number 2 appears. Okay, so what is the probability that number 2 appears? So there is only one possible event that 2 will appear, and that has a number of total number of events are 6 in a pair of die. So the probability of success that 2 will appear will be 1 out of 6. Okay, and it states here that at no time. So probability of success that 2 will appear will not happen. Okay, so there are how many number of trials? 4. This denoted as Rn, and then Rx will be success in that trial is 0 because 2 will not appear. Okay, so you'll have here 4, C 0, and then the probability that 2 will appear is 1 out of 6. Okay, and the chance or the success is 0, and then 1 minus P will give us 5 out of 6, or 5 all over 6, and N minus X will give us 4 minus 0, so that's equivalent to 4. Using your calculator, so the probability that 2 will not appear is 48.23%. Okay, so next, continuation from that problem. So probability that 2 will appear twice. Okay, so again, the probability of 2 will appear is 1 out of 6, 1 all over 6. Okay, and then it will appear twice, so this is X. Okay, so this will be the number of success in a given trial, and the number of trials still 4. So N is 4. So you'll have here 4, C, and then X is 2. Then the probability of success is 1 all over 6, and X is 2, and then 5 all over 6 is 1 minus P, or simply this is the Q, or probability of failure. And this will be N minus X will give us 4 minus 2. Using your calculator, you'll have an 11.57% that the number 2 appears twice. So moving forward with our example 3. So find the probability that in 4 tosses of a pair die, the number 2 appears 4 times. Okay, so n is 4, x is 4. Okay, and then the probability of 2 will appear is 1 over 6, and the probability of failure will be 5 out of 6. Okay, so that will give us 4, c4, and then 1 all over 6, x is 4, and then 4 minus 4 is 0. Okay, so you'll get 0.08% chance that 2 will appear 4 times in the 4 tosses of fair die. So okay, for the next problem, find the probability that in a family of 3 children there will be no boy. Okay, so having a child, it's either have a female or a male, or a girl or a boy. Okay, so that's a 50-50 chance, so 1/2 for the boy, that's the probability of getting a boy, and a probability of getting a girl is also 1/2. So find the probability that there will be no boy. Okay, so there are 3 number of trials, so 3 is n, and then x is no boy, so that is 0. So you have 3 c 0, and then 1/2, that is the probability of getting a boy, and the chance is, or success in that trial, 0. And then probability of failure, which is 1 minus p or 1 minus 1/2 is still 1/2. Okay, and then n minus x is 3 minus 0, so that gives us 3. So you have using your calculator, you can have an answer of 12.5%. Okay, that's the probability or chance of not getting a there will be no boy in the family. Okay, then at least one boy, continuation with problem number 4. Okay, so at least one boy, so x is 1. Okay, so at least one boy. Okay, so there could be 2 boys, or probably all of them are boys. Okay, so you'll have this first uh, equation, so you'll have a chance of success of 1 and a failure of 2, so 1 out of 3. Okay, and then this is 3 minus 1, and then for second option you'll have at least, okay, at least 1 here, so you'll have 2 boys. Okay, so and then for this third you'll have 3 boys and no girls. Okay, then simplifying this, you'll have an 87.5% chance. Okay, then at least one boy and one girl. Okay, so for this particular problem, at least one boy or 2 boys, 1 girl. Okay, and then at least one boy, so let us consider first the 1 boy 2 girl. Okay, we'll have this equation here. So for the probability of getting a boy, that is 1, and then probability of failure is 2. Okay, and then for this one, probability of boy, okay, success of 2, and then probability of failure is 1. Okay, then you'll have a chance of 75% of getting at least one boy and one girl. Okay, so here another problem. So a lot of 100 batteries is known to contain 10 defectives. Okay, 5 batteries are selected at random. So, and each battery is replaced before the next battery is selected. So what is the probability of getting at most 2 defectives? So maximum number of defectives is 2. Okay, so you'll notice here says each battery is replaced before the next battery is selected. So the total sample will always be 100, or your denominator will always be 100. Okay, so if there are no, you'll consider first is that there will be no defective, or then the other one will be one is defective, and then the other one will be at most two defective batteries. So n is 5, so 5 of them, or 5 of the batteries are selected. Let us consider no defective, so x will be 0, and 10 defectives up of 100 will be your probability of success, and then 90 out of 100 will be your probability of failure. Okay, so this is raised to x. Okay, so that is x is 0, and then 5 minus 0 is 5. Then there will be one defective here. Okay, so the probability of defective is 10 out of 100. X is 1. Okay, and then 90 over 100. Okay, and then this is 5 minus 1, then 5c2. So number of probability of success is 10 over 100, and then x, or success, will be 2, and then 90 out of 100 will be your probability of failure, and then this is 5 minus 2. Okay, so the simplifying this, you'll have a 99.14% probability of getting at most two defective batteries. So multinomial probability. Okay, so multinomial probability. So the binomial experiment becomes a multinomial, okay, if each trial has more than two possible outcomes. Okay, the formula here, okay, there's something wrong with this one. Okay, this is called the partition or partial probability. Okay, so it should be written as, okay, x1 factorial, x2 factorial, and so on, and this will be n factorial. Okay, so let's see this one. Okay, so the probability of getting the first outcome, n1 times, is probability of success 1 raised to n1. Okay, the probability of getting the second outcome is probability of success of 2n2, and so on. Okay, so you'll have this formula. Okay, going back to this formula, okay, should be n factorial, then x1 factorial, x2 factorial, and so on. Okay, up to xk factorial. Okay, you'll notice here I have provided n1 factorial, n2 factorial, multiplied by n3 factorial, and so on, multiplied by the product of probability of success raised to n1, raised to n2, and so on. Okay, this is just similar to this one. Okay, but then kindly correct this one, okay, with this formula, and you can substitute x1 here, provided you also substitute x1 here. Okay, so let's have the sample problems. Okay, so the complexity of arrivals and departures of planes at an airport is such that computer simulation is often used to model the ideal conditions. For a certain airport with 3 runways, it is known that in the ideal setting, the following are probabilities that the individual runways are accessed by a randomly arriving commercial jet. So at runway 1, the probability of success is 2 all over 9. Runway 2, probability of success is 1 out of 6. And runway 3, we have a probability of 11 all over 18. So what is the probability that 6 randomly arriving planes or airplanes are distributed in the following fashion? 2 airplanes in runway 1, 1 airplane in runway 2, and 3 airplanes in runway 3. Okay, So you'll notice here, these are the x1, x2, and x3, and n, or number of success, will be 6. Okay, so based on my formula here, so I could say that this is n1, n2, n3. Okay, or if you're going to go back to this formula, you can say that it is x1, x2, and x3, and so on. But then these are the x1, x2, x3. But then on this given formula, the denominator here are n1. So the exponent of their probability of success will be n1. Okay, going back. So you'll have this solution. So that is n factorial, okay, all over n1 factorial, n2 factorial, and then n3 factorial. And these are the p1, which is probability of success. Okay, so p1 n1, okay, p2 n2, p3 n3. Okay, if you have 4 runways, you'll have p4 n4, and so on. Then you'll have an n4 here. Okay, so by simplifying this equation, or this function, you'll have an 11.27% probability of getting this fashion. Okay, suppose that we have a bowl with 10 marbles. Okay, so those are 2 red marbles, 3 green marbles, and 5 blue marbles. So we randomly select 4 marbles, okay, from a bowl with replacement. Okay, so every time you get a marble, you place it back. Okay, so what is the probability of selecting 2 green marbles and 2 blue marbles? So the number of trials will be 4. You're selecting 4 randomly marbles, and then successes will be 2, 2, okay, from green, and 2 from blue. Okay, so n factorial all over n1, n2, n3. Okay, so there are 3 colored marbles here. So these are the probability, or these are the number of trials, which is 4, and these are the number of success within those trials. Okay, so 0 for what you call this, red marbles, 2 for green, okay, and then 2 for blue. So the probability of getting a red marble is 2 out of 10. The probability of getting 3 green marbles is 3 out of 10. And the probability of getting 5 blue marbles is 5 out of 10. Okay, so the probability of success of getting a red marble is 2 out of 10, which is n1 is 0. Okay, so there are no success, or it is not specified to get a red marble, so that's why it is 0. Okay, so 3 out of 10, that is the probability of getting a green marble with an exponent of n2. Okay, based on this given. And then 5 out of 10, this is the probability of getting blue marbles. Success is 2. Okay, so simplifying this one will give you a 13.5% chance of getting a probability of 2 green marbles and 2 blue marbles. Okay, so next will be hypergeometric probability. Okay, so the difference between binomial and geometric, hypergeometric geometry is, in binomial distribution, sampling must be done with replacement, but then in hypergeometric distribution, okay, it does not require independence and is based on sampling done without replacement. So these are just the definitions. So our random sample size of n is selected without replacement from n items, and then of the n items, K may be classified as success and n minus k are classified as failure. So the number x successes of a hypergeometric experiment is called hypergeometric random variable. So the probability distribution of hypergeometric variable is called hypergeometric distribution. Okay, so this will be your formula. These are simply combinations. So kx, so kcx, okay, and then this one is n minus k, cn minus x, and then this will be capital N, then cn, where x is always a positive integer. Okay. So suppose an urn contains 7 balls with 3 red balls and 4 blue balls. If we are going to take 5 balls at random, what is the probability of selecting 2 red and 2 blue? Okay, so there are total of 7 balls. Okay, and then you'll have a probability of getting 2 red balls. So that is, there are 3 red balls in the urn, so 3c3, 3c2 I mean. And then for the blue balls, you need to get 3 balls, 3 blue. Okay, so that will give us 4c3, and then the denominator below will be the total uh, number of balls and then the total number of uh, balls taken. Okay, so that will give us 7c5, and the probability of getting or selecting 2 red balls and 3 balls, 3 blue balls is 57.14%. Okay, oops. Okay, so this one. So suppose that 5 cards are randomly drawn without replacement from a 52 card deck. So find the probability of obtaining 3 red and 2 black balls cards. So in a 52 deck of cards, okay, you have 26 red and 26 black. Okay, so for the red, so there are 3 obtained cards, 3 red cards, so 26c3, and for black you'll have 26c2. Okay, and then the denominator will be the total. Okay, so the capital N and the small n. So capital N is 52 and the small letter n is 5 cards. So 52c5, and you'll have a 32.51% chance of getting a probability of 3 red and 2 black cards. Okay, so a faculty student committee is to be selected at random from 3 students and 4 faculty members. The committee is to consist of 2 persons. Find the probability that a committee will contain no student. So there will be no student. So there are 3 students, so that will give us 3c0 and then 4c2. Okay, so it contains 2 persons. So we'll have here, and then the total of those will be 7 from the selection, and then 2 of them will be selected, so you'll have 7c2 for the denominator, and you'll have a 28.57% of probability that the committee will not contain a student. Okay, and then continuation for problem 3, find the probability that the committee will contain 1 student. So we'll have 3c1 and 4c1. Okay, so at least you can see here, and then the total number of person or faculty and students 7, and then the selection will be 2, so 7c2. You'll have a 57.14% that the committee will contain 1 student. So the committee will have 2 students, no faculty, so 4 faculty, there will be no faculty, so 4c0, 3c2, and then 7cc2. Okay, so you'll have 14.29% chance of probability that the committee will contain 2 students. So from a lot of 10 missiles, 4 are selected at random, okay, and fired. If the lot contains 3 defective missiles, what will that missiles that will not fire? What is the probability that all 4 will fire? So 7 missiles, there are 3 defective, so 7 are not defective, so 4 will all fire, so there will be no defective here, so you'll have 7C4, so 7 a number of non-defective, and then 4 of them will all fire, and then for the defective you have 3 defectives, and then none of them were fired, okay, and then these are the totals, so 10C and then 4, okay, so you'll have a 16.67% probability that all 4 will fire. Okay, so you'll have here at most 2. Okay, so when we say at most 2 will not fire, so there could be all of them will fire, at least one is or one will not fire, or 2 will fire. So you have here all 4 will fire, okay, and there will be no missile that will not fire, okay, and then if one of them will not fire, so you have 7C3. These are the number of success, and then this will be your failure for not firing, so 3C1, okay, and then for at most 2 will not fire, so you'll have 7C2, okay, and then 3C2. Then you'll have a 96.67% chance that at most 2 will not fire, okay. Mm. Yan. Negative binomial probability, okay. So let's consider an experiment where the properties are the same as those listed for a binomial experiment. So with the exemption that the trials will not be repeated, okay, until a fixed number of successes occur. Okay, so this will be similar to the formula for binomial. This will be x minus 1 c k minus 1, and then this is the probability of success and probability of failure. Okay, so let's have here in an NBA championship series, okay, the team who wins 4 games out of 7 will be the winner. Suppose that team A has a probability of 55% chance of winning over team B, and both teams A and B face each other in the championship games. So what is the probability that uh, team A will win the series 6 games? Okay, so 6 games, so let's go back to the formula. So x, okay, will be what will you call this? X will be your number of trial, and k will be the number of success, okay. So x will be the number of trials, so 6 will be x, so x minus 1 is 5, okay, and the number of trials will be 4, okay, who wins 4 games, so that will be your k. So 4 minus 1, or k minus 1, based on this formula, okay, so that will give us 4 minus 1, that gives us 3, okay, and team A will win, okay, so winning chance is 55%, and that will be 4, okay, 4 out of 7, so 4, and then probability of failure, which is 1 minus p, or 1 minus 0.55, will give you a 45% chance, okay, and then this will be k minus x, or what's the formula? Kx minus k. Okay, x minus k. So still this will be 6 minus 4. Okay, and then 18.53% chance that A will win the series in 6 games. Okay, don't be confused with these 5 and 3. These are based on your formula. Those are x minus 1 and k minus 1. So x is 6, so 6 minus 1, you have 5. And then for k minus 1, okay, so 4 minus 1, you'll have 3. But then in the exponent, k is 4, and then x minus k is 6 minus 4. So that is 4, 6 minus 4. Okay. So continuation, what is the probability that team A will win the series? So 4 games out of 7. So continuation of those of problem 1, what is the probability that team A will win the series? Okay, so based on this given information on the problem, okay, we will be using the information that team A and team B play a sequence of games until one of the team has won our number of games. And because we want team A wins the 4th game, okay, before team B, so you must have a limitation of R, A is greater than or equal to X, and then greater than or equal to 7. So X is less than or equal to R, and then X is greater than or equal to 7. Okay, using that limitation, okay, we get a probability. Okay, so probability x minus 1 and k minus 1. So for the 4th game, so 4 should be, this should be 3 and then 3. Okay, so it should be 3c3. Okay, because 4 minus 1. Okay, and then this will be 4 minus 1. Okay, so this should be 3c and then 3. Okay, this is the 4th game, 5th game, 6th game, and then the 7th game. Okay, so should be 0 0.55 0. Okay, so this should be 3c3. Okay, then this will be the on the 5th game. Okay, so 5 minus 1. Okay, and then 4 minus 1. Okay, and then for this one is 4 minus 1, and then this will be 6 minus 1, then 7 minus 1, and then 4 minus 1. Okay, so you'll have a 60.83% chance of winning. Okay, so there's a correction here for 3c3. Then for this problem, okay, so if both teams face each other regional playoff series, the winners decided by winning 3 out of 5 games. So 3 out of 5. Okay, and then 3 out of 5 games. Okay, so winning 3 out of 5 games, the probability team A will win. So you'll have this equation, so that will give us 3c3, 3c2, and then 4c2. Okay, so you'll have a 59% of 59.31% chance or probability that A will win the playoff in the 3 out of 5 games. Okay, so another problem, the probability that a student pilot passes the written test for a private pilot license is 0.7. Okay, so fail will be 0.3. So 1 minus this success is 0.3. Find the probability that the student will pass the test on the 3rd try. Okay, so 3rd try. Okay, so that will give us x will be 3 and k will be 1. Okay, so 3 minus 1 is 2 and 1 minus 1 is 0, so 0.7. Chance on the third try it should be 1, and then on the probability of failure will be 2 out of 3. Okay, so this will be 3 minus 1, and then you'll have a 6.3% chance. Okay, before the fourth try. Okay, so chance before the fourth try, so possible it passes on the first try, failed on the second, and on the third it failed. Okay, so 1C1. Okay, and then probability of success is 1, and then failed is 0 for the first try. Okay, then for the second try you'll have 0.71. Okay, and then 1. Okay, so 2C0 based on the formula. Okay, so you'll have a 97.3% chance. Okay, before the fourth try. Geometric probability. Okay, so you'll have this formula probably. Probability of success and failure, x minus 1, where x are all positive integers. Okay, so for a certain manufacturing process, it is known that on the average 1 in every 100 items is defective. So what is the probability that the fifth items is the first defective item found? So the probability of success is 1 out of 100 in if that is defective, and then probability of failure will be 99 out of 100, and then this 4 is based on your formula that is x minus 1. Okay, so fifth or item will be 5, will be your x, so x minus 1 is 5 minus 1, but that gives us 4, so you have a 0.95% chance. Okay, Poisson probability. Okay, Poisson probability counts the number of successes in a fixed interval of time or within the specified region. It is often used to model the number of random occurrences of some phenomenon in a specified unit of space or time. Okay, so numerical values, random variable x, and the number of outcomes, interval, specified region are called Poisson experiments. Okay, so example of these are the number of chimney fires in Valenzuela factors during January, the number of people arriving at the emergency room at the hospital during 8-hour shift, the number of raisins in a slice of raisin bread, and the number of kernels of corn that failed to pop in a 3.5 ounce bag of microwave popcorn. Okay, so the number of outcomes occurring during Poisson experiments called a Poisson random variable, and its probability is called Poisson distribution. Okay, so these are just some definitions. Okay, so formula. So probability of observing exactly x number of occurrences. Okay, this is lambda, then time. Okay, x factorial. E is your mathematical constant. You can use your calculator. Okay, so that will give us 2.7183. This is the approximate value. You can use your calculator. Okay, so lambda is the average number of outcomes per unit time. Okay, so this t is time and lambda is per unit time, so time and then time will be cancelled out. Okay, let's use the formula, or let's see some example. So during the laboratory experiment, the average number of radioactive particles passing through a counter in 1 millisecond is 4. So radioactive, that gives us lambda. And what is the probability that 6 particles enter the counter given milliseconds? So 6 particles will be our x number of occurrences. Okay, occurrences per unit of measure. So as you'll notice here, 6 particles in a given millisecond, so 6 per millisecond, so 6 particles per milliseconds. Okay, and take note of the formula. Okay, so lambda is 4. Okay, and then x is 6 particles, and then e is a mathematical constant, and then negative 4. Okay, and then 6 factorial, and that gives us 10.42% of uh, probability. Okay, so the number of cars arriving at a run gasoline station follows a Poisson distribution with mean of 3 cars every 3 minutes or at 10 minutes. What is the probability that exactly 1 car will arrive in the next 10 minutes? Okay, so lambda will be 3. Okay, and then exactly 1 car will be your x1. Okay, and then lambda is 3, and then x will be 1, and then e negative lambda time. Okay, then that gives us 1 factorial, so you'll have a 14.94 percent probability that exactly 1 car will arrive in the next 10 minutes. How about 2 cars will arrive? So simply changing the x from the given previous solution. Okay, so lambda will be 3, x will be 2, then e raised to negative lambda time, then 2 factorial. Okay, so you have 22.40% chance of probability that exactly 2 cars will arrive in the 10 minutes, in the next 10 minutes. Okay, 3 cars. Okay, you just simply change the x here. Okay, so same procedure, lambda will not change. Okay, how about this one? So the owner of a tree farm specializes in growing pine trees and selling them for Christmas trees. They are grown in rows of 50 trees, and the owner has found on the average that about 4 trees per row will not be suitable to sell. Assuming that the Poisson distribution is applicable here, find the probability that a row of trees selected for shipment will contain 2 unsaleable trees. Okay, so 4 trees per row. Okay, so that will give us the lambda. Okay, 4 trees per row, and then 2 unusable or unsaleable trees will be our x. Okay, so you'll have 4 for lambda, and then 2 for x, e raised to negative lambda. Okay, and then this is x factorial. Okay, so you'll have 14.65%. So from the past experiences, a basketball club owner knows that about 4 games on average will have to be postponed during the season because of rain. Find the probability that this seasonal game will have to be postponed because of the rain. So this season, no game, so there will be no game, 0 game will be postponed, so that is x, and your lambda is 4. Okay, so 4 raised to 0, and the 0 factorial, e raised to negative 4. Recall that 0 factorial is always equal to 1. Okay, and that will give us 1.83% probability. 56. Okay, so example 5, suppose that on average 1 person in 1000 makes a numerical error in preparing his or her income tax return. So if 10,000 returns are selected at random and examined, find the probability that 6, 7, or 8 of them contain an error. So these are your x's, x1, x2, and then x3. Okay, and you need to solve for the lambda. Okay, so the lambda for every 1000 person is so the lambda, this is 1 per 1000. So then in a 10,000, what should be the lambda? Okay, so by equating those information, you get a lambda of 10. Okay, so since lambda is then 10 lambda, then 6 will be x, and then e raised to negative 10 lambda 6. Okay, plus, okay, next 7 is x, and then 8 is x. Okay, and then you'll have a 26.57% probability.